Hi, welcome to Organic Chemistry. I'm Katie. For me, one of the hardest things about organic chemistry is just how intimidating it looks. Today, I'm going to try to hopefully break that down so you guys can understand it a little bit better. In fact, I'm going to break down all of these complicated structures into the most basic organic element, carbon. Carbon is often called the element of life, and one of the key reasons for that is because it's in, if not all, almost all organic molecules. And one main property that allows carbon to be used in this way is its ability to bind to a lot of things. So carbon has 4 valence electrons that are available for bonding. This means that it shares its electrons with other molecules. And it can share these electrons with a wide variety of other molecules, including other carbons, oxygen, hydrogen, nitrogen, sulfur, phosphorus. Those are all elements that you're going to see a lot of in organic chemistry. As carbon binds to these other molecules, it makes bigger molecules like you saw on the last screen. And so as these structures form, they are normally called functional groups. So other carbons, they might form methyl, ethyl. When it binds to oxygen, it could form esters, ethers, ketones, carboxylic acids, and the list goes on. The most basic molecules that you'll find in organic chemistry are called hydrocarbons. These are molecules that are made up of hydrogen and carbon. I know, very creative. Some of these hydrocarbons are alkanes, and these are carbons that are linked together by a single bond. The suffix that are used to name these are ane. Then you have alkenes, which are carbons that are linked together by a double bond, and the suffix used to name these are ene. And then you have alkynes. These are carbons linked together by a triple bond, and the suffix for this is ine. I know it's kind of hard to say. So we just had the suffix of the name of this hydrocarbon molecule that indicated the type of bond that was used to link together the carbons. Now, the prefix of the molecule is based on the number of carbons in the molecule. So if there's only 1 carbon, it's going to be called meth. 2 carbons is eth, 3 prop, 4 bute, 5 pent, 6 hex, 7 hept, 8 ox, oct, 9 non, 10 dec. And this can keep going. As you can see, we can start to look at what some of these molecules actually look like. So methane really is just a carbon, and it's going to be saturated with hydrogens. So like I said before, carbon has those 4 valence electrons that are going to be shared with some other molecules. So in its simplest format, that carbon shares its electrons with hydrogen. And so that's the simplest. Methane, it's just 1 carbon and 4 hydrogens all around it. Then we can move on to ethane, which is going to have 2 carbons and hydrogens all around. That's also saturated, but once you go into ethene, where there's a double bond, it's no longer saturated with hydrogens because those carbons kind of eliminated 2 hydrogens in order to create that double bond. So then we have ethene, and similarly with the triple bond, we have ethine. We can keep doing this and just adding that same nomenclature that we just talked about with propane. And normally what you'll see as you start adding in carbons is organic chemists will start drawing them with just little lines. Carbon really is the backbone of a lot of organic molecules. And so instead of drawing a bunch of C's and a bunch of letters, we just stopped using it. So when you see just lines, any little corners of those lines is going to be a carbon. So here we have butane, and you can count the little corners and the ends, 1, 2, 3, 4, and that's butane. So 4 carbons. When you add it, but what if I add the double bond in a different place? Instead of on the end, it's in the middle. Or what if I draw the carbons in different ways? This is where organic chemistry leads, and it's often not as simple as just zigzag lines and counting the corners. You can see here The naming of these molecules changes as well, and we will definitely get into this more in the following lectures. But just as an example, here you have transbutene, and that's because the double bond is in the middle of the molecules, and the two carbons coming out of the ends are going in different directions. And then below that I have cisbutene, and you can see that the two carbons coming out at the bottom are going in the same direction. So trans and cis, that's how we name the stereochemistry of these molecules. Also, since that double bond is in a different location than just butene, you have to name it that way as well. And so we'll indicate that by saying trans 2-butene or cis 2-butene. That little 2 is indicative of where that molecule is. And I know you might be thinking, well, what if I switch it around? Isn't it technically on number 3? Or wouldn't that be 3 to 4? Since butene is a small molecule, you can rotate that and it's the same thing. So if you switch it around, thinking that the double bond is on the third carbon is the same thing as it being on the second carbon. And if you have it going from 3 to 4, that's the same thing as it going from 1 to 2. Just as a disclaimer, we don't normally say 1-butene. It's just assumed if it's butene that 1 is understood. It's on that first carbon. Similarly, we can have carbon molecules that aren't just hydrocarbons on their own, but they could be connected to other organic molecules that have oxygen or nitrogen in them. This is called a substituent. And we will definitely get into this more with other functional groups, but for now we're going to focus on the hydrocarbon substituents and how to name those. So once again, it goes by the number of carbons. Here, the R that I'm drawing, that's used to indicate the rest of the molecule. That's how I think about it. So when you see an R, that just means there's something else there. So you can imagine one of those big, scary molecules here, and what I'm drawing is just the substituent that we're focusing on now. So just like what we saw before, it's using those same prefixes for the number of carbons, where 1 will be methyl, 2 ethyl, 3 propyl, and 4 butyl. And you can see how you draw it, it's the same way. Well, what if we want to move those carbons around, especially with 3 and 4, propyl and butyl? We can rearrange that and make completely different molecules. So you can see here I'm drawing a couple other hydrocarbon substituents that still have 3 carbons and still have, or 4 carbons, but it's no longer propyl and butyl. These are other substituents, and I have their names listed here: isopropyl, isobutyl, sec-butyl, and tert-butyl. This is kind of just something you're going to have to memorize because these are different molecules with their structures. And this is just one example of a true functional group, which is, in my opinion, one of the key fundamentals to organic chemistry, is learning these functional groups and eventually their properties and what that means, what it does having that as part of a molecule. And you'll learn that butyl is very, very different from tert-butyl in terms of what it binds to, what that means for the molecule. And it's really, really interesting once you get into it, but for now, this is just an introductory lecture. You're really just going to need to know what these are and be able to identify them. So, back to those big, scary molecules. How do you get from just hydrocarbons to stuff like this? The answer is functional groups, and we are going to get into this into the next lesson and talk about more than just carbons and hydrogens and look into what happens if we have a functional group with oxygen or nitrogen. So I hope you learned a lot. I hope the big, scary organic molecules seem a little less scary now. And if you have any questions, feel free to reach out. Thanks so much for watching. Have a good day.